Okay, I hope I'm audible to all my students who are attending this online lecture for the Intermediate Mathematical Methods for Economics course offered currently in semester 2 of BA Honors Economics. In this particular online lecture, I'm going to start with the discussion of the 2025 question paper which has come up at Delhi University for the Intermediate Mathematical Methods for Economics. Okay. Um, it's a 90 mark question paper. And in this particular online lecture, I'm going to start with a discussion of the first problem of this particular question paper. Okay. If students go through the guidelines or the instructions, the question paper has 9 questions in total. All questions are going to carry equal marks. Okay. It's a 90 mark question paper. So there are 9 questions, and all these questions are for 10 marks each. Simple calculators are allowed in the intermediate mathematical methods for economics course. Okay, rest of the instructions are quite basic instructions. So I am going to start with the discussion of first problem. The first problem is based on the concept of eigenvalues, which I have covered in quite depth in my lectures on linear algebra, specifically in my lectures on matrices. Okay, so let's quickly start with the discussion of the first question from the 2025 question paper in this particular online lecture. So let's read question 1, part A. Let A be a n cross n matrix. Suppose A has a real eigenvalue lambda greater than 0. Find the eigenvalues of the matrices A plus the identity matrix, A square plus the identity matrix, where I is an n cross n identity matrix. We are given that A is an n cross n matrix. It has an eigenvalue lambda. We need to find eigenvalues for A plus I and A square plus I. So let me quickly come to the whiteboard to solve this particular problem. I am just writing the main heading for clarity. This is Delhi University exam 2025. Name of the course is Intermediate Mathematical Methods for Economics. I can just write Intermediate MME, which is currently offered in semester 2 of BA Honors Economics. We are starting this particular lecture with discussion of question 1. Within question 1, we are looking at part A. We are given that A is an n cross n matrix with a real eigenvalue lambda greater than 0. Okay, we need to find out the eigenvalues for A plus I and A square plus I. Okay, so let's quickly work out this particular problem. So I can write that since lambda belonging to positive real numbers, because lambda is greater than 0, it's a positive real number. Since lambda belonging to positive real numbers is an eigenvalue, of the matrix A, therefore by definition determinant of A minus lambda I should be equal to 0. We have done this in our lectures on linear algebra. Okay, if lambda is an eigenvalue, determinant of A minus lambda I should be equal to 0. Now, let me try and create A plus I. So what do I do? Within the determinant, I can add and subtract I. So adding and subtracting I within the determinant. The purpose of doing this is to create A plus I, which is this, because I need to find the eigenvalue for A plus I. So what I do, students, I have added I, but then I also subtract I. So within the determinant, I just added and subtracted I. How can I further write this? I can write this as A plus I, and within this, I can take I common. So I can write minus lambda plus 1 times I. Now, if lambda is a eigenvalue for A minus lambda I is 0. What is the eigenvalue for A plus I? You can clearly see that A plus I minus lambda plus 1 times I is equal to 0. Which implies what? Which implies that lambda plus 1 is an eigenvalue of lambda plus 1 is an eigenvalue of A plus I. I'm repeating it again. If lambda is an eigenvalue for A minus lambda I determinant is 0. Based on this logic, I added and subtracted I. The reason I did it was to create A plus I. And now what I've got is A plus I minus lambda plus 1 times I equals 0. So if I follow the pattern, I can clearly say that lambda plus 1 is an eigenvalue for A plus I. Just as lambda was the eigenvalue for A, lambda plus 1 is an eigenvalue for A plus I, which is what I had to find out. So this is one answer. Now let's work out the eigenvalue for A square plus I. So if I move forward to the next page to find eigenvalue for A plus I. To find the eigenvalue for A square plus I. We have already found the eigenvalue for A plus I. Let's work out the eigenvalue for A square plus I. Now, since lambda is an eigenvalue, since lambda is an eigenvalue for the matrix A, I can say AX is equal to lambda X. Again, this is by definition of eigenvalues. I can say AX is equal to lambda X. If I multiply both sides by A, I can write multiplying, because I need to create A square. Multiplying both sides by A, I can write A into AX is equal to A into lambda X, which implies A into AX is A square X is equal to A into lambda X. I can write lambda times AX using the distributive property. Okay. Recall the distributive property in multiplication. A into BC is equal to AB into C. This is the distributive law. This is the associative law. Let me correct myself. This is the associative law we do in matrix multiplication. Associative law in matrix multiplication. Okay. So what I've done is I've taken lambda outside and AX together. And now what is AX? AX itself is lambda X. So I can write A square X is equal to lambda times. I can make a substitution. Instead of AX, I can write lambda X from here. So this becomes A square X is equal to lambda square X, which I can write as A square X minus lambda square X is equal to 0, which implies I can take X common, so it makes it I can take X common, so it makes it A square minus lambda square times X equal to 0. Or even from this equation, students can see, compare this equation with this equation. If lambda is an eigenvalue for AX is equal to lambda X. Okay. Now we need to find the eigenvalue for A square. I got A square X equal to lambda square X. So from this, I can say that lambda square is an eigenvalue for A square. Okay. See, Lambda is an eigenvalue for A, that means AX is equal to lambda X. Similarly, I got A square X equal to lambda square X, which means lambda square is an eigenvalue for A square. I need to find the eigenvalue for A square plus I. If lambda square is an eigenvalue for A square, it implies lambda square plus 1 will be the eigenvalue for A square plus I. Okay, so again, this was using the properties of eigenvalues, which I've covered up in my lectures on linear algebra. So I'm revising it again. We have to find the eigenvalue for A square plus I. Since we are given, this is given to us that lambda is an eigenvalue for matrix A. That means by definition, AX is equal to lambda X. I multiply both sides by A. The reason I do it is because I want to create A square. So A into AX is equal to A times lambda X. This gives me A square X is equal to, I use the associative law, which makes it lambda times AX. I substitute the value of AX, which is lambda X. I get lambda square X. Now A square X equal to lambda square X means lambda square is an eigenvalue for A square. If lambda square is an eigenvalue for A square, what will be the eigenvalue for A square plus I? Lambda square plus 1. Okay, I can even go back to the previous page and students can clearly see that, look at the pattern. If lambda is the eigenvalue for A, what is the eigenvalue for A plus I we got? The eigenvalue for A plus I we got was lambda plus 1. See? That means to A, the moment I add I, the eigenvalue gets added by 1. Same pattern I've repeated it here. See? For A square, the eigenvalue I got was lambda square. So for A square plus I, the eigenvalue I will be getting will be, the moment I've added I, the eigenvalue gets added by 1. So this is my answer for the eigenvalue for A square plus I. So hoping all students have understood how we have solved this particular problem. I stop in this particular lecture. In the next lecture, I'm going to start with the discussion of question 1 part. So I hope all students have enjoyed this short lecture on eigenvalues. Any doubts, you can unmute your mic and ask, or you can get in touch with me for doubts on call or WhatsApp, or you can mail me your doubts at divineschoolof economics@gmail.com. This is where I stop in this lecture.